My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 568. In this lecture, we will try to understand optimizer's hill descent in 3D and contours. Just like the way we have seen the examples in 2D, let's see the examples in 3D. Here for the 2D examples, if you notice, we said W is a scalar. Just try to recall my lecture number 566. We said W is a one-dimensional scalar. Let's assume W is two-dimensional vector. In deep learning case, your W is with many dimensions. In the case of deep learning, your W is with many dimensions because you have tons of weights, you have here lots of weights. Your WKIJ is of thousands of weights. But we try to understand the way when W is one dimensional, what happens in two dimensions. We can visualize up to three dimensions. We can't visualize any further. Let's assume my W is a vector of two dimensions. That is W equal to W1. Yes, as I told you, WKI is of thousands of weights. Let's assume your W is of two-dimensional vector, W equal to W1, W2. This is what is my W1 axis? This is my W1 axis and this is my W2 axis. I can say this is my x-axis, my y-axis and my z-axis. Z-axis here is loss, isn't it? What is my z-axis here? Z-axis here is loss because your loss is function of W. W itself is a vector. Your loss will change if W1 changes or W2 changes. This is basically going from scalar to vector, isn't it? Here I have my weight W1, I have my weight W2, my z-axis here is my loss. What is my z-axis? Z-axis here is loss, and what you see is convex, isn't it? This is a convex loss function. This is convex loss function. This is generalization of the generalization of parabola that we discussed few lecture in our previous lectures. I can say this is a parabola, isn't it? This particular function, this one is what is this? This is generalization of, I can say, generalization of parabola. What we see here is this one is basically, what is this? This is 2D plot, isn't it? This is 2D plot. The same thing we are seeing in this is, I can say, it's a 3D. It's a 3D plot. Very interesting, isn't it? Very interesting, very simple. This is also convex. That's important. Everything above this one, I can say, just say this one, everything above is one region, means everything above this one, inside this particular, everything above is one region, and everything below outside, this is another region, isn't it? Everything below or outside, this is another region. Everything above this curve, everything inside this, everything inside this is one region, everything outside this is another region. That's what we discussed even for parabola, isn't it? Suppose this, as we are saying, this is a convex function. Suppose if you take any two arbitrary points in this particular region, in this point and this point, if I join them with this particular line, the resulting points which are in this line are plane, all of them are in same region, isn't it? They are in the same region. This is an example of convex loss function. When your weights are two-dimensional, yes, when your weights are two-dimensional, that is W1, W2, your loss function is plotted on z-axis. We notice these lines here. Just see these lines. You can see the lines here. What are those lines? Just let me highlight this line, this line, this line, these lines. These lines are, what are those lines? These lines are known as contour lines, isn't it? Though these are known as contour lines. And what the mean here, what's the meaning of these contour lines? Let's take one line. This line basically says, the way I plot contour lines is very interesting. Just we will try to understand. The way I plot contour lines is very interesting. Let's call this is let me say this is length. Let's call this is length, and this is width, and this is height, isn't it? Easy for us to visualize. So you take all the points which are of same height. Yes, just take all the points. This point is very important. I will repeat. Take all the points which are of same height. Isn't it that? Let's take I'll take all the points which are of same height. Suppose how can I take? This is the point. Let me say these are the points of same height. Yes, I'm assuming this is a point, this is a point, this is a point, this is a point, this is a point. They're of same height, isn't it? They have same height. They have same height. I'm connecting all the points which are at same height, because visualizing in 3D is very hard, because you can't plot 3D on 2D. People are trying to visualize your 3D function in 2D, because this is 2D surface, is it not? What is this? This is 2D surface. This is 2D surface W1, W2. Yes, you are visualizing 3D in 2D surface, isn't it? Because this is 2D surface. This the surface here I have. So they use contour plots as a way to visualize. They use contour plots as a way to visualize 3D function just using the 2D plots. All the points which are at same height, that is important. All the points which are at same height, connect them and draw the shape. All these points have same height or same loss, isn't it? Contour means what? For example, in the on the contour, for example, I can say all these points have same height. Again, all the points which are in this particular contour are the same height. All the points which are on the contour same height, isn't it? That is the basic idea, isn't it? All the points which are at the same height, connect them and draw the shape. All these points which are in the contours have same height or same loss. This bottom plots, just see the bottom plots in this one. The bottom plots that you get here is called contour plot. Let me show other contour plot. I just Google search for convex 3D functions. Let me say this is convex 3D functions. Now I am looking in 3D. I'm looking that 3D functions in 2D. Just see, because what is this circle says? This circle, this is my W1. Just see here, this is circle, isn't it? Just see, this is my circle. Yes, this is my W1. This is my W2, isn't it? These are W1 and W. When this is W1, this is W2. All these points are at same height. Just see, all these points are at same height. All these points are at same height. That's what I'm saying. All these points are of same height. This is other way of visualizing 3D data in 2D surface. Look at this. This is more slightly complex, isn't it? Let me assume this is W1. This is my W1. Let me say like this. This is my W1. This is my W2. All these points have same height with these points. Just see, all these points have same height. Similarly, all these points, there is another set of points. All these points are of same height. Let's take a slightly complex example. This example has multiple minima and multiple minima. There is a minima here, minima. Yes, there is a maximum. There is another maximum. This is, what is this function? This is non-convex function. If you take, this is, what is this? This is W1. This is W1, then this is W2, and on z axis, I can say it's a loss, isn't it? This is equivalent to example, just this is, I can say this is equivalent to this example. This is equivalent to this is equivalent to this example. This is in 2D, this is in 3D. Just you are generalizing 2D to 3D. Here also you have multiple maxima, multiple minima. In this particular complex function, you have multiple maxima and multiple minima. This is example where you have multiple maxima, multiple minima. This is 3D generalization of 2D plot, and this is non-convex function. And look at the contours like this. Just see here you have multiple minima. Just look at the contour like this. When you have contour plots like this, you have minima here, isn't it? If you have contours like this, you have minima here, isn't it? But what is in the case of non-convex functions? You have multiple minima and multiple maxima. Just you can see the contour plots. In contour plots, you can identify where is the minima, isn't it? It is simple and straightforward. Yes, just see this one. This is another example where you can see the maxima, minima. This here you have z values. What is my z value here? Just say this one. Here z value is something like 0.600, means all these points are at this particular height. Z equal to 1.50, all these points are this particular height, all these points are this particular height. Yes, you can visualize these contour plots with this particular z values, isn't it? Even just try to recall saddle point, what we discussed about saddle point. What is minima for this saddle point? If you go for this direction, if you take in this direction, yes, if you come here, this is a minima. If you come from here, this is a minima. That's why I'm saying this is minima, isn't it? If you take same thing here in this particular direction, in this, if you take along this axis, this one is maxima, isn't it? They are intersecting, therefore this point is saddle point. If you observe, here is your gradient is 0, slope is 0, like 2D case, isn't it? For slope, for saddle point also, slope equals 0, neither maxima. This is 3D generalization of saddle point. If you take this one is minima, this is horse saddle, isn't it? In the case of horse saddle, this is the minima, isn't it? This is the minima. Again, what is the maxima? If you go like this, this is the maxima. This is intersecting point is known as saddle point. Just try to recall, this is y equal to x cube function. If you look at this slope here is 0, isn't it? It is neither maxima nor minima. F of x equal to x cube has a saddle point at x equal 0 because slope here is 0. This is neither maxima nor minima. Between these, even here also, between, just see here what it says. This is also Wikipedia. Saddle point lies between two hills, two mountains, isn't it? Here, just see, this is saddle point is here. This is one mountain. This is another mountain. In between two mountains, I have saddle point, isn't it? Just go through this lecture. This is simple and straightforward lecture. Just try to understand. If you have any difficulty, please keep a comment. Thank you very much.